Hello, everyone. Thank you for giving me this opportunity to present some of our recent work in your group and have a hopefully fruitful discussion afterwards. So I'm Masoumeh Keshavarz and I'm working at KU Leuven in Belgium. Yeah, the weather is nice today. And today I will be talking about shedding light on the optoelectronic and structural properties of halide perovskites. So I started working on this material class after I finished my PhD in 2016. When I moved to Leuven from Netherlands, I used to work in the high field magnet lab in Nijmegen, and then I came to Leuven to do my postdoc. I started working on halide perovskites. Our group is a multidisciplinary group consisting of chemists, physicists, and material scientists. The chemists grow the material, the physicists work on the optoelectronic properties and also structural properties, or let's say fundamental properties of the material, together with the material scientists. Then we engineer the materials based on the results we get, and these are all towards optimizing the material for applications. So when I started working on halide perovskites, I came with the idea of writing a project on it, on the exploring the optical, electronic, and structural properties of halide perovskites under extreme conditions. And this project was granted for 3 years of FWO grant, which was just finished in 2020, end of 2020. The motivation for that work was to use beyond state-of-the-art techniques to determine material properties under extreme conditions, which would be the high magnetic field or external field, electric or magnetic field, and very low temperatures down to 4.2 Kelvin. We wanted to access and determine photophysical properties that makes perovskites so unique, and also explore, engineer, and tune novel perovskite materials towards stable and environmental friendly. Can you still see my presentation?
Yes, so the second slide with the
yes.
pyramid.
Yeah, sorry, it was just out for 1 second. Towards higher efficiencies. So actually, perovskites provide a playground for chemists, physicists, and material scientists, since they have been discovered by the Russian mineralogists. They take chemical formula of ABX3. A is a cation, B is a metal, a heavy metal, and X, normally physicists know them as oxides, but can be other groups as well. So they take a cubic structure where A sits at the corners of the cube, and a B sits in the middle, and X sits in the center of each face of the cube. Depending on which atoms or molecules are in these structures, perovskites show different interesting properties, such as colossal magnetoresistance, which means that their electrical resistance changes when they are put in a magnetic field, which is used in the microelectronics, superconductivity, ferroelectricity, charge ordering, spin-dependent transport, high thermal power. And also the interplay of structural, magnetic, and electronic properties are commonly observed features in this family. However, what I will focus in my talk today on will be on halide perovskites. So what are the halide perovskites? They take, again, ABX3 formula, but instead of oxide or other groups, on the X sits a halide, which is a chloride, bromide, or iodide. In the A, as the cation, can sit an organic or inorganic group. The organic can be methylammonium or formamidinium, and the inorganic group can be cesium. B is heavy metal like lead or tin. Halide perovskites show several spectacular properties, such as high absorption coefficients, direct photogeneration of free carriers, efficient charge transport, long carrier diffusion lengths, wide bandgap tunability by either the cation A or the halide X, substituting these atoms, or and also they show low non-radiative recombination rates in polycrystalline films. Apart from their tunability from the atomic substitution, they can also be tuned geometrically, and their morphology can be tuned. They can be from different, their sizes can range from quantum dots, for example, the 0D to 1D nanowires, or 2D perovskites, layered perovskites, and also the 3D millimeter size single crystals. Depending on the atomic groups, the morphology and geometry of the perovskites, they can be interesting for several kinds of applications. For example, in LEDs, lasers, memories, photodetectors, transistors, batteries, or even sensors. Since 2010, when they were used in the solar cells and they showed kind of 3% power conversion efficiencies, lots of groups started working on their fundamental properties and also their application in solar cells. And lots of publication has been reached. You can see published. You can see here in the statistics in the Web of Science, which I just put the word halide perovskite, and you see how many publications and citations were raised during such a short time. Also, after their use in the solar cells and the 3% power conversion efficiencies, people have been working on it, and there was a huge jump to now reaching more than 25% power conversion efficiency in single junction, or more than 28% in tandem configuration with silicon. So there are some pros and cons of perovskites. So the benefits of them is that they have wide band gap. Their flexibility in the structure can help for tuning their properties. They also have very high absorption coefficient, and this makes it that we can have a very thin layer of it into the devices. So we can have semi-transparency in the cells. We can have thin films. They are lightweight, and also you can make them actually on a bench in the lab from a solution. So their processing costs are extremely low compared to other semiconductors. They offer a significant advantage over silicon in photovoltaic applications, because perovskites react to a broader range of the visible light. And also this means that they convert more sunlight to electricity than silicon does. But there are some drawbacks, and there is always some drawbacks. So the most important one, to my opinion, is their stability. So they have poor long-term stability upon exposure to heat, moisture, oxygen, and light. And even light, for example, the combination of these can increase their degradation paths. For example, light can actually promote the degradation paths from the defects and so on into the system. Then is the device performance or reproducibility. So over a large area, it's not unified. And also the last one is the toxicity, because there is lead in this material, and lead is a toxic element. If there is leak in the cells, then there is danger for the environment, having lead leaking out. Now let's look at the library of the material that we have available in molecular imaging and photonics in Leuven, photonics group in Leuven. So how we grow the crystals, let's say, is we just mix the right ingredients in the right solvent, and then we heat it and we cool down slowly, and the crystals form. That easy. And even a physicist like me can grow them in the lab. Following the recipe, actually. So depending on the ingredients and also the solvent and the procedure where you make the material, we could achieve the lead-based perovskites from nanometer scale to millimeter single crystals, as you can see here. Also, we could have wires, cubes, and even the layered perovskites with the 1 layer, 2 layer, and 3 layers, tuning the number of the layers, as well as lead-free perovskites and double perovskites, which I will talk about it at the end of my talk. So the outline of my talk is divided into 3 parts. In the first part, I will talk about the transport measurements of single crystals of lead-based perovskite under illumination. Then I will talk about their structural properties and phase transitions. And then I will talk about the double perovskite, the tunability of their structure, and as well as their optoelectronic upon substitution, atomic substitution. So in part 1, the state of the art when I started this project was that, first of all, there was a lot of various numbers reported for mobility, and the measurements were mostly performed by fast spectroscopy measurements, which in a very short time, you put a lot of intensity of the light into your system, and then you look at the relaxation of the charge carriers, and like that, you can extract the mobility. However, you can also affect by light the system, by the intense light onto your system. Most of the measurements were performed at room temperature, where you cannot access the scattering mechanisms into your system because of the high thermal energy. So the motivation for this part was, first of all, to do charge transport under steady-state illumination, which is the real working condition of perovskites in the cells or photovoltaic, and then access the mobility and density of charge carriers, identify dominant scattering mechanism as a function of temperature, and also probe magnetoresistance in these low mobility semiconductors. So the setup that we used, the experimental setup that we used in this part is, first of all, this is a bitter magnet. I don't know if you can see my pointer. This is a bitter magnet, the gray cylinder that you can see here. And then in this part, I will only focus on metal ammonium lead bromide, whose picture is on the top right, and the orange crystals. We did these measurements for metal ammonium lead bromide and metal ammonium lead iodide single crystals, where we evaporated gold contacts on the crystals and then mounted them on the chip carriers and connected them with silver paste. Then we mounted the chip carriers into our insert, which is coupled to a laser through a fiber. And the laser that we use is a 373 nanometer laser to make sure that we are above the bandgap, exciting above the bandgap. This insert is mounted in a cryostat. So if we look at the sketch of the sample, it's shown here. We send the current through the longest path of the sample. We measure the resistance along the current path, and we call it RXX. You will see it in the plots later on. And we measure the current or the voltage perpendicular to the current, which we call it RXY. And that is the Hall signal in the presence of a magnetic field. The magnetic field is always perpendicular to the plane of the sample. So the current will be sent through by Keithley, and the measurements, the signal will be detected through lock-in amplifiers. Here you see, so just again, I repeat that these measurements are done on our metal ammonium lead bromide, the orange sample. So we measured a Hall signal in the dark. Before that, to make sure that we are in the ohmic regime, we measure the IV curves, and you can see we apply a current which is in the ohmic regime. The Hall signal is linear, the Drude model we can use, and from that we can extract the carrier concentration, and from the carrier concentration also and resistivity of the sample, we can extract the mobility. So via the Hall measurements, we have access to the carrier concentration and mobility. In dark, we extracted the mobility for the sample. On the right plot, you see the experiment which has been performed under steady-state illumination. So here the laser is on. We measure the Rxx, you see on the left axis, and on the right axis is Rxy. The Rx is the magnetoresistance in the presence of the magnetic field, and it shows the classical orbital effect, the quadratic dependence, and the Rxy is linear. We extracted the carrier concentration, which is 1 order of magnitude higher than in the dark under illumination. I must say that for the dark measurements, we extracted the carrier concentration for the bulk sample, but under illumination, because the penetration depth of the light is only 80 nanometer, we consider it as a sheet conductivity. So now let's look at the temperature dependence of the resistance for example, methylammonium lead bromide. We measured between 4.2 and 100 Kelvin because we wanted always to stay in one same structural structure from temperature, the resistance changing, scaling with temperature linearly until it reaches a minimum amount, which shows a maximum conductivity. We can extract a maximum conductivity from this point, and then it starts increasing exponentially. So we can identify two distinct regimes, regime 1 and 2 here. In regime 1, we say that the carrier the transport is governed by the hopping of the carriers, and we can actually, from Arrhenius plot, we can extract the activation energy for that. You see in the inset. Then we performed these measurements at different temperatures, and we extracted the carrier concentration and mobility for each temperature. So here you see on the right side, you see on the left axis the carrier concentration, and on the right axis the carrier mobility as a function of temperature. The carrier concentration is increasing until it reaches its maximum and then is constant. However, from the temperature dependence of the mobility, we can actually identify the scattering mechanism in the system. So we see that in regime 1, the mobility scales with temperature with the power law of 3/2. And this is an indication of ionized impurity scattering. When we increase the temperature further, which is regime 2, we see that it scales, the mobility scales with temperature with the power law of -3/2. And that is an indication of acoustic phonon scattering being the dominant scattering mechanism in the system. Now let's look at the magnetoresistance as a function of field. So it shows, in general, we measure the magnetoresistance for different temperatures. For methylammonium lead bromide here is shown. And we see this classical orbital effect, which is the quadratic behavior. However, if we zoom into the lower temperature and lower field data, we see a negative magnetoresistance, which is actually because here in this regime, the carriers are just, the transport is governed by the hopping of the carriers, and the small magnetic field is increasing the carrier path length, and by moving them, and then when we increase it further, it scatters them. So here is enhanced field-induced carrier transport, actually. If we measure the magnetoresistance as a function of magnetic field, if we plot magnetoresistance as a function of magnetic field normalized to the zero field resistivity, this is referred to as Kohler plot. And in the Kohler plot, all the curves at different temperatures, actually, all the curves which are merging, they are following the same scattering mechanism. So we see that below 20 K, the curves are merging on each other, and above also they are merging with different slope. So these two shows, this is another indication that we have two distinct regimes here. And if we plot the square root of the magnetoresistance as a function of temperature, this is related to the inverse scattering rate of the carriers. And if it's changing linearly or it scales with temperature linearly, is an indication of acoustic phonon scattering to be the dominant scattering mechanism. And here we approve our measurements, the first one independently. So the take-home message is that the transport under steady-state illumination is actually the technique to address perovskite's intrinsic optoelectronic properties such as mobility, carrier concentration, diffusion length, and scattering time. And one can identify the underlying scattering mechanism using these measurements. In the part 2, the state of the art was that the structural transitions and phases were reported again differently for the same material, for the same temperature ranges, and also why is it important to know the structural properties of the material? Because changes in the structure can have effects on electronic properties of the material. It can change the band structure, and from that, the optical properties. Also, it can change the phonon structure, which affects the exciton binding energy. So there is a strong quest for defining or identifying the transition temperatures in the crystal structure for different phases accurately. And here our approach was, for the first time, we used the thermal expansion measurements or dilatometry measurements, which has an accuracy of 0.1 nanometer, below 0.1 nanometer or below angstrom accuracy. So the motivation here is to probe thermal expansion of single crystals from 4.2 to room temperature, determine the exact phase transition temperatures, also maybe the sample quality, could be a check for sample quality, and by using some complementary techniques, we can actually identify the phases of the material as well. So on the right side, on the top, you see a picture of a dilatometer or thermal expansion measurement. One can measure thermal expansion as a function of two different parameters, either temperature or magnetic field. Through these measurements, one can access information such as the superconducting transitions, quantum oscillations, or structural transitions. So here you see a closer picture of the setup. It's very simple and user-friendly. You mount your crystal between two copper plates, and then you measure here on this figure. You see better on the right side at the bottom, you see better how the capacitance is measured. So the capacitance is measured between these two plates. And any changes in the one axis of the crystal can be A, B, or C. So it's a linear thermal expansion, can actually be measured through the capacitance measurements. The capacity will be measured through a bridge, and then the length will be calculated using this formula. And what we actually see later on in the plots is delta L over L. Delta L is the changes in the length during one axis of the crystal. Mostly and mainly in this study is C-axis, along the C-axis, and L is the room temperature length of the crystal, so it's normalized to the room temperature length, the changes that we see. Now let's take one of the most known crystals, which is methylammonium lead iodide, in which the transitions are known, the transition temperatures are known in literature, and see if our technique can access such transitions. We measured in this plot, you see the delta L over L as a function of temperature, and on the right axis, you see the derivative of delta L over L, which is just the thermal expansion coefficient. Any abrupt changes in the delta L over L as a function of temperature can be an indication for the phase transition, structural phase transition. And we see for this material, it has been predicted around 160, there is a transition from tetragonal to orthorhombic. We exactly see the temperature in which is predicted. So this method is accurately accessing the transition temperature. We also did transport as a function of temperature, transport measurement, and we see at the transition temperature, which is around 160, there is this jump in the signal and shows actually that we can access this information through electronic transport. Another aim to perform electronic transport was that we wanted to see how does the electronic properties of the material changes when the structure changes. And we see a reduction in the carrier concentration going from tetragonal to orthorhombic phase for this material, 20% reduction. Now let's just change
Excuse me?
Sorry?
I have one question.
Yeah.
Here, when you're using which method you are using here to identify the phase transition? Which method you are using?
So on the left side, we are using the thermal expansion measurement, which is using the dilatometry. And on the right side, we use transport measurement, which is just measuring resistance as a function of temperature.
Thank you very much. Thank you.
So if we now replace the iodide with bromide, we see more complex transition scheme, and we see that at room temperature is cubic. Then there is a transition from cubic to tetragonal. Also, it is known for metal ammonium lead bromide that in the tetragonal phase, the different directionality of the Ma group can actually induce a little bit of changes in the tetragonal structure named tetragonal 1 and 2. This has never been seen via XRD or X-ray diffraction methods, but here this method, thermal expansion, is so sensitive that can even observe such things. One can observe such little changes in the structure. So we were happy to see that, and then later on it goes from tetragonal to orthorhombic. So here you see a zoom into the position of the phase transition temperatures. It is very accurately identifying the transition temperatures. Now we took two different batches of the material, the single crystals of metal ammonium lead bromide. So one is batch A is freshly synthesized, and batch B is 1 year old, just kept under ambient conditions on the table. So we wanted to know how does this degradation of the material affect the structural properties. So we know that the metal ammonium lead bromide takes cubic at room temperature, is cubic at room temperature, and then goes to tetragonal and then to orthorhombic. Now, looking at these two plots and comparing them together, we see that actually metal ammonium lead bromide, which was from batch B and old, never reached cubic phase. And also the phase transitions are not as sharp as how they are in the freshly synthesized ones. And this we attribute to the presence of islands of phases within the other phase because of the defects into the system. We also approved these measurements through photoluminescence lifetime measurement, in which batch A showed much longer lifetime compared to batch B, which means that the crystal is of higher quality. And also the anisotropy factor in the batch B was much larger.
Excuse me, can you go back to the previous? Yes. So you're saying with the aging process, you have a structural change, or you have also some extra impurities that come?
So we think that actually these defects which are forming on the surface and then later on penetrating to the depth is actually changing the structure, so that it's so the order is so much less that it can never reach the cubic phase, and also the structures are not, you see that the transitions are not that sharp anymore, so which means that you have something which slows down the thermodynamic into the system.
Okay. Okay, thank you.
So we think that's the defects which is doing that. Now let's just change methylammonium, like the A group, to formamidinium and see how does that change the structure of the crystals. By changing just Ma to Fa, which is slightly of lower ionic radius, we see that the crystal, for the formamidinium-lead iodide, we see that the crystal is not perovskite at room temperature anymore, but if you heat it to 120 Celsius, it becomes black and perovskite, but at room temperature it's not conductive, and it's not in a perovskite phase. So we did the thermal expansion measurements nevertheless, and we see that by getting help from our colleagues from Denmark, they did these high-resolution X-ray diffraction measurements. We could identify the phases of the material at each temperature range. So we observed the transition from a high order hexagonal to a lower symmetry hexagonal for the formamidinium-lead iodide, but below 50K also we see a structural change, which we couldn't access that through XRD measurements, so we don't know what is the phase, or is it distortion, or even ferroelectric domains or whatever. Sorry. And also we see two large negative thermal expansion regions in this material, which has never been observed before, with a very large negative thermal expansion coefficient compared to the known materials. This can also open more applications for perovskites. Then going from iodide to bromide, again, the phase diagram is much more complex compared to the iodide ones, and we see the cubic phase at room temperature. Then by cooling down the system, we reach the tetragonal phase. We identified these structural phases through XRD measurements, and the temperature in which the accurate temperature in which the transition is happening through dilatometry measurements or thermal expansion measurements. We couldn't identify the structures in these regions where we have these structural changes in the thermal expansion through XRD because it's not that sensitive, and we think that these are some distortions of the octahedra or the orientation of the formamidinium group, which changes the structure. And then by cooling further down, we reach the orthorhombic phase. Now let's conclude for this part that the linear thermal expansion of bulk single crystals of halide perovskites has been done, and this thermal expansion is one of the most accurate methods to determine phase transition temperatures. However, we need a complementary method to identify the exact phases of the crystals, the structure of the crystal. And structural changes visible in transport experiments under steady-state illuminations as well. And we compared the optoelectronic properties together, and we see the structural changes are changing actually the optoelectronic properties. Now let's move on to the last part of the talk, which is about the double perovskites. So why the name double perovskite? Because in the double perovskites, lead is actually substituted by a monovalent and trivalent atom, is silver in this case and bismuth. So we have cesium-2, which is the A cation, then B is silver and bismuth, and bromide is the halide, bromide 6. So here the only difference is that we have exactly same octahedras, but in this case we have alternating octahedras, one centering around silver and one centering around bismuth. So this silver bromide and the octahedra silver bromide, the gray one, and the purple one is the bismuth bromide. Why double perovskites? They are lead-free, first of all. there is no lead in it. They are more stable compared to the single perovskites, but there is a drawback that their power conversion efficiency is not so high in solar cells. And that is attributed to their high Urbach energy, giant electron phonon coupling constant, and so on, and low mobilities also. However, their application in the X-ray detection has been proven to be very, very efficient, and they are very sensitive materials to X-ray, so with higher sensitivity than ever reported. So what we can do beyond the state of the art is that we can actually do a bit of atomic substitution, because this material has even wider range of possibility for atomic substitution, with all sites being available. Then one can manipulate the optoelectronic properties through this substitution, and they are highly tunable. They can be also used in devices, in the X-ray detectors, for example, already shown that they are effective, but can be tuned their properties so that they are also effective in solar cells. So the motivation for this part of the talk is that, first of all, we want to evaluate the role of alkali substitution in cesium-2 silver bismuth bromide 6, tune their X-ray response. Can we make them even more sensitive to X-ray detection? And we want to determine and tune optical and structural properties. So for these measurements, we use the slightly different approach. We use temperature-dependent photoluminescence measurements. For that, this is again a magnet, but inside is a cryostat. In the cryostat, there is an insert. The insert is coupled to a fiber. The fiber has two parts, two lines, one line in the middle, through which we are exciting the sample with a laser. And there are a lot of other fibers, like 11 smaller fibers around the excitation path, through which we collect the photoluminescence light, which is coming from the sample. And the detection path is on the other side of the image. You cannot see it. And these are the electronics controlling the setup. So through these kind of measurements, one can access the photophysical pathways in perovskites with a combination of optics, steady state, and transient photoluminescence measurement. Then one can access the electron phonon interactions and information on the nature of the band gap in the material. So these are how the crystals look like. These are the cesium silver bismuth bromide crystals. This is their XRD, and this is their structure, as I explained. Here below in the plot, you see the absorption on the right side and photoluminescence of these materials on the left side at room temperature on the top and at 77 K at the bottom. As you can see, the photoluminescence at room temperature is much more broad because of the scattering of the carriers in the system due to thermal energy. So if we measure their photoluminescence at different temperatures ranging from 4.2 Kelvin to 300 Kelvin, which is the room temperature, and we fit each of these curves with the Gaussian, we can extract the information such as PL peak center or full width half maxima of the Gaussians. By analysis of the full width half maxima of the Gaussians as a function of temperature and using this model, one can access the electron phonon coupling constants. For example, one can see which one is the dominant scattering mechanism by looking at the contribution of each of these terms. And also one can access the exact coupling constant, the electron phonon coupling constant. What we could conclude from these measurements was that the coupling constant, the optical phonon coupling constant for this material is more than 200 milli-electron volt, which is much, much larger compared to the single perovskites because they are in the range of 50 to 70 milli-electron volt. And here, this shows that these ionic crystals actually are the soft solids, let's say. So the interplay or the interaction between these two octahedra is causing this giant electron phonon coupling constant. Then we looked at their IV characteristics, in which at room temperature we could see all three regimes: the ohmic, which is the linear, then when we increase the voltage, we reach the trap filling limit, which is the regime where we are filling the traps. And then when we increase the voltage further, we reach the Childs regime, which is where when all the traps are filled already. At low temperature, within our measurement window, which is we can only apply 200 voltage, we could only observe the linear, the ohmic regime. Then we exposed them to X-ray and we measured their photoresponse. And as you can see, they have a large photoresponse upon X-ray exposure, and even much larger when you go down in temperature. So this is for pure cesium silver bismuth bromide. Now, let's take the mother compound, which is the cesium silver bismuth bromide, and I emphasize and replace 2%, only 2% of cesium with rubidium, either rubidium or potassium or sodium. So upon this little substitution, one can see that the response upon X-ray exposure for the rubidium substituted one is much larger than the mother compound, which is the black curve, as you can see here. So we succeeded to tune their properties by just substituting 2% of the cesium with rubidium. Now let's look at their optoelectronic properties. How do they change? Here you see an example of the photoluminescence measurement as a function of temperature for rubidium. If we analyze all these curves for all the samples and extract all the information, such as PL peak center and full width half maxima, we can see from the derivative of the PL peak centers, we can see if any abrupt changes are happening. And any abrupt changes in the PL peak center is an indication of the phase transition, in which we see here around 120 Kelvin for all materials, within a 10 Kelvin window, more or less. And we confirm that through dilatometry measurement and also high resolution XRD measurements, that these are actually phase transition. And also at low temperature, we see a structural change, which we couldn't confirm it through XRD measurements, and we think that this is just structural distortion and it's not a phase transition. And these are the Varshny fitted with Varshny equations and the parameters extracted. So now let's look at their full width half maxima as a function of temperature. The coupling constants are extracted through these measurements, and we see that is more or less constant for the optical phonon scattering. However, the coupling constant for acoustic phonon scattering is increasing upon substitution, which we can attribute that to the smaller ionic radius of the alkali metals which are substituted, the cesium. And that we confirm through high resolution XRD measurements. Then we actually performed transient photoluminescence measurements in different time window and as well as detection window. So the time windows range from picosecond to microsecond, and we also measured in different wavelength window for the detection path. So we measured from, let's say, 500 to 800 nanometer at each wavelength one curve. And through that, one can access the decay associated spectra of the for each lifetime. And for each lifetime, we can identify from where it is originating, from which wavelength it is or which energy it is originated. First of all, I must say that the longest lifetime, which is attributed to the the free carrier recombination lifetime, was longer or 3 times more for the substituted materials, which can explain the X-ray response for the rubidium, for example. However, the mobility was reduced for the potassium and sodium, but for the rubidium, the mobility was constant, same as cesium. which was measured through time domain terahertz measurements. To conclude, we put the result of all these measurements in different wavelength detection windows and time domain terahertz measurements. We could actually propose this model for the system. We could prove that there are large polarons forming in these systems, which is not strange looking at their the giant electron phonon coupling constants. Then there are defects in this system causing the very fast decay lifetimes. Then there are some fast and slow decay lifetimes, which are, one is originated from the bound and unbound excitons, and the other one, the slow one, is originated, which is within the microsecond range, is originated from the free carriers. With that, I would like to conclude that, well, the electron phonon coupling constants and photophysical pathways in halide perovskites can be identified through temperature-dependent, time-resolved, and steady-state photoluminescence. Unabsorption and the lead-free double perovskite materials are suitable material for X-ray detectors, and one can even, by tuning their structure, reach higher responses, X-ray responses, and this opens a way to tune their structures so that we can achieve actually higher power conversion efficiencies also in solar cells. With that, I would like to thank all people who contributed to this work, from KU Leuven, Radboud University, Max Planck Institute in Dresden, Aarhus University in Denmark, the funding agency FWO who funded my project, and KU Leuven, as well as EMFL, who granted our proposals for high field measurements, and of course you for your attention.
Thank you very much for the very nice presentation. Are there some questions? Maybe I can, Andrea, please.
Hello, can you hear me?
Yes.
We can hear you, but not very well. Yeah, try to speak clearly.
Okay, so good morning. Thank you for the nice talk. It's really nice to see a woman in science. So first of all, it was really, really nice and understandable. I'm pretty new to this topic, but I don't know if I got a little lost. In the first part, you talk about nanocrystals.
Yes.
Was it related, or better? Are those some kind of quantum dot from perovskites, or it's different?
So the measurements that I performed throughout this talk and I talked about, they were all on large single crystals of millimeter size. But perovskites have different range of morphology. You can actually tune their the crystal size from quantum dots to have quantum dots to up to millimeter size. So you can have cubic quantum dots or nanowires of 200-300 nanometer size, or micrometer size single crystals, or millimeter size single crystals, and in different morphologies. Even you can have cubes, you can have elongated shapes like rods, or even nanowires. So mostly in the applications, people are using either quantum dots or films. But of course, for fundamental studies, the single crystals are best because you can exclude already a lot of external effects into the system. And that's why we are choosing to study mostly on the single crystals.
Okay, I thought, I don't know why I thought you were talking about some quantum dots as well, because you say that it's possible to fabricate quantum dots and
yes.
wires. But
for applications, that's best actually. Yes.
And in the last part, the third part, you say something like the application was XRD, or X-rays interaction and things like that. But in the very first two, it didn't got clear for me which was the main application or like the main idea.
In the first two parts were mostly pure fundamental studies, but in the last part, we actually made the devices and tested them under X-ray exposure. And in the X-ray field, actually, it's an ongoing research that people are looking for higher sensitive material to reduce the dose of the X-ray applied to the patients, or for example, in the security, in the airports, they want to reduce the X-ray exposure dose, and that's why they are looking for more sensitive materials. And these double perovskites show that they are really highly sensitive to X-ray, and they can be used in future X-ray detectors. Already the panels are made already and tested.
Okay, thanks again.
No worries.
May I come back to the measurements that you did with 1-year-old samples? I was surprised by the structural changes after 1 year only. So my question is a bit, I mean, if you want to use this for photovoltaic purposes, for example, how do you prevent this? Do you put a coating on your materials so you don't have these changes?
Yeah, indeed, that's very much an ongoing topic in the field, because the stability is under question, and there are a lot of degradation pathways proposed for this material that can be avoided by either passivating the surface or packing the cell such that there is no leak, or making everything oxygen free, air free, humidity free, and pack it and then bring it to the application. But there are also some chemical processing approach which people are doing in order to reach it, but it's not yet concluded what would be the best. The only thing which is known is that they are not stable, and that is the biggest issue to bring it into the industrialization at the moment.